Alright. Let's take a look at the heart. So like I said, I don't spend that much time in blood, but the heart of it, what we're going to be talking about are the vessels. I'm sorry, yeah, we'll talk about the red blood cells, and specifically the hemoglobin in the vessels. So we'll save the best for last, because that one can be fairly difficult when we explore the concept of gas exchange. But the heart, when again, looking at the heart, and like I said, most of this is review, so I'm going to kind of speed through it if you don't mind. But if we take a look at the size of the heart, basically the size of a closed fist. And it pumps about 10,000 times per day. The whole purpose of the heart is really for the transport of the blood, which is going to contain all the things that I talked about earlier. All the gases, nutrients, the hormones, the proteins, and all the stuff that is present in blood. The whole sole purpose of the heart is just to provide that function, is to move blood through. We're going to have blood that's going to be circulating through the rest of the body, and we're going to have blood that's circulating through the pulmonary circuit, which is going to be the lungs. So looking at the location of the heart, about 2/3 of it is really going to be to the left of the midline. So here you can see the midline of the body. 2/3 of the heart is on the left side of the body. You'll see the apex of the heart is actually pointing down left. The base of the heart is going to be up here at the top portion. There's a slight tilt to the heart itself where you can see the orientation of it. Looking at the layers of the heart, if we were to take a cross section of it, you'll see we have the pericardium, para meaning outside, cardium related to the muscle tissue, the cardiac muscle fibers that you can see that are present. And the pericardium, again, is the outside fibrous layer that surrounds the heart. It fits it kind of like a glove, and it actually prevents the overexpansion of the heart itself. So if you ever look at heart surgeries, they can see the white fibrous layer that covers it. They have to cut that through in order to be able to see the heart contained within. So the pericardium is actually divided into two layers, where you have the fibrous layer and the serous layer. Fibrous being the outside portion, and then the serous layer being a bilayer, where you have the parietal layer just tucked underneath the fibrous layer, and then you have the visceral layer that's flush against the heart muscle. And in between, you're going to have serous fluid. This is the pericardial cavity. And that whole purpose of that cavity is to have pericardial fluid, about 35 to 40 milliliters of fluid that flows around. And that serves to lubricate the heart as it expands and contracts and expands against that fibrous pericardium. This is where the term pericarditis comes from. Any inflammation, any bacterial inflammation of the heart starts to create excess fluid in that area. So now you've got this bag, the pericardium that's on the outside, and you've got the heart pumping against it so it can't overexpand. You start to build up all this excess fluid in it, and now the heart can't expand as much. So pericarditis, which is again that inflammation of that cavity, starts to affect how much that heart can fill up and pump blood out. The other layers contained within, you can see the visceral layer, and then you can see the epicardium. The epicardium is a layer just right underneath the serous layer. You'll get the myocardium, which is the thickest portion. This is where we're going to have our cardiac muscle all contained within. This is going to serve as the contractile portion of the heart that's going to be doing all the muscle motion. And then the endocardium, which is going to be the innermost layer that's exposed to the blood as it's flowing through the heart itself. So the endocardium is also typically called the the endothelium. It's the inner layer of the heart. Looking at the divisions of the heart, you can see that while the heart works together to pump blood, you're going to see two different chambers. You'll have 4 total chambers. You have 2 atria and 2 ventricles. So the atria, as you know, we know are up at the top, the ventricles down at the very bottom. And the whole purpose of the atria and ventricles are different chambers to be able to move blood in. So as you know, the atria will pump first, the ventricles will pump second. So you're going to see the exchange of blood as it moves through, blood coming into the heart and blood coming out of the heart. And this whole mechanism that's in place is meant to direct blood out to those respective circuits, in which you can see, like I said, 2 atria and 2 ventricles. Each side, 1 atrium and 1 ventricle, is going to be responsible for the systemic circulation. The other one's going to be involved for the pulmonary circulation. I'll draw that out for you, where we have systemic and we have pulmonary. Pulmonary being the right side of the heart, and systemic being the left side of the heart. Systemic being pumping out to the rest of the body. And if you were to take a look at the systemic circulation, here you can see that's carrying oxygenated blood out to the body. So left ventricle, when we look at a lot of the clinical measures, they're looking specifically for left ventricular function. If you ever get an echocardiogram, they're looking at left ventricle ejection fraction. How much blood can you pump out the left ventricle? Obviously, you want the left ventricle to work hard enough to be able to deliver blood to every portion of the body, all the way down to the feet, to be able to deliver blood back to the heart. Through the right side of the heart is going to allow blood to enter back in, that's blood returning from the systemic circuit, to pump it back out to the heart, the lungs, hence why it's called pulmonary circulation. The thing about in between the atria and the ventricles are as well as the other valves, the other input and output of the heart are going to be valves, and they're going to regulate the blood flow in and out of the heart, and into the ventricles, and into the atria and out into the ventricles. So this is going to govern, when we look at these valves, the direction of blood flow. So the first that we're going to discuss are the atrioventricular valves, also known as AV valves. I'll be calling them AV valves for short. And these are going to be the valves in between the aorta, atria, and the ventricles. So while we see them at the top over here, you can see these are the atria, here are the ventricles. We're going to see that on the next slide over. Right atrium, right ventricle, and here you can see our AV valve. The differences in the AV valves between the right side of the heart and the left side of the heart, you can see the right will have what's called tricuspid, while the left side will have bicuspid. So what exactly is a cuspid? Cuspid refers to a structure similar to that of a leaf. So here we can see on the right side of the heart, we've got 3 leaflets, 1, 2, 3. While the bicuspid valve on the left side will only have 2 leaves. So the reason why they call the bicuspid valve, you might also have heard as the mitral valve, is the bishop's hat, which is called a mitre. And that is 2 leaflets that come together, and hence where that name came from. The other characteristic for the valves, I'll talk about in the next slide over. The semilunar valves, on the other hand, are the ones towards the back, of which we have the aortic valve and we have the pulmonary valve. So pulmonary valve for the right pulmonary circuit, aortic valve for the left circuit. So these you can see right up next to each other, and they will be opening and closing at different times when the AV valves are opening and closing. So as we start to learn more about the sounds of the valves, we'll be able to see the 2 different valves that open and close at different times. And these 2 images show you very well AV valves opening while our semilunar valves are closed. AV valves close while the semilunar valves are open. So these are going to contribute to the different sounds of the heart, the lub-dub, if you will. And from those sounds of the heart, we'll be able to determine the movement of blood through the heart, the different things that can take place when normally listening to heart sounds. One thing that we'll also learn about the governing of blood flow from one side to the next. Here you can see a cross-section of the heart where we can see the anterior view. We'll talk a good chunk, especially when in our heart lecture, is the movement of blood from one chamber to the next. So how are we going to get blood moving from the left atria over to the left ventricle? And the big idea behind all of this is going to be pressure. Pressure that's involved in moving blood from one side to the next. We're going to learn about the mechanism of squeezing of the left atria, which will push blood into the left ventricle. We'll learn about how the left ventricle fills up. And as that fills up, how do we squeeze blood out to make it out into the aorta to be able to shoot out to the remainder of the systemic circuit. So again, pressures that are going to govern how we get one chamber to pump blood into the next, and how we get the ventral to pump blood out into the systemic circuit. Looking at the valves, again, as I mentioned earlier about the pressure, we'll learn about the AV valves. The AV valves are one-way valves actually all of them are one-way valves. Both our AV valves as well as our semilunar valves. But the AV valves have specific anatomical structures that prohibit it from reopening. So what we can take a look at in our AV valves, here you can see an example of the bicuspid valve. Again, one thing I want to go back to, one way that I remember which one is which. We know that tricuspid is on the right, bicuspid on the left. Something I always remembered, a little mnemonic for myself, was try right, bi left. And that way you can remember. Try right, bi left. Now, here we can see the bicuspid valve for the left side of the heart. You can see the two leaflets here. The AV valve, the way that's going to work, in order to get blood to pump from, this is where the left atrium, and then this is where the left ventricle, I'll be calling LALV from now on, at least when I write it down, left atrium to left ventricle. In order to get blood to flow from the left atrium to the left ventricle, I'm going to have to exert a good amount of force to open up that valve. So you'll learn about the pressures that are involved to be able to push blood out into the next ventricle. So in order to get that, I'd have to squeeze the left ventricle to push blood through. So as blood makes its way from the left atrium to the left ventricle, here you'll see the bicuspid valve just open up. And that's not going to prevent blood from flowing through. In fact, blood should flow through easily. And what's present on the ventricular side is the presence of muscles. And we know there's muscles as well as tendons involved. And here we have papillary muscles that are present along the wall, ventricular wall itself. And these muscles are combined with what are called chordae tendineae. These are tendons that project onto the leaflets themselves. So it kind of works like an upside down umbrella where when blood flows from the left atrium into the left ventricle, the valve is opened. And so flow should be unimpeded as it flows into the left ventricle. Now what happens when the left ventricle starts to squeeze and the left atrium relaxes? What that's going to do, it's going to force blood only one way. So blood can only flow from left atrium to left ventricle. As this pressure starts to increase, what that's going to do is going to close this portion up. And blood is going to push up against the cusps and cause it to flap right back up. And the reason it's not going to flap right back open is because the chordae tendineae are literally holding those valves shut. So here, in between, in our AV valves, typically you'll never see blood flowing in the reverse direction. So the prevention of blood flowing back into the prior chamber allows blood to flow out through the next chamber in place. So if this were to draw a very loose diagram of it, this would be our aorta, and this is going to be our aortic valve in place. That's only going to allow blood to flow out in that direction. Now, looking at the semilunar valves, both our pulmonary valve as well as our aortic valve, they actually don't have any anatomical support, meaning they don't have the papillary muscles, they don't have the chordae tendineae to hold it back in place. But if you were to take a look at the structure of the valves are a little bit harder. Due to that lack of anatomical structures, the semilunar valves are typically the ones that need to be replaced more often, specifically the aortic valve. The aortic valve is one in which if they notice the aortic valve is not closing the way it's supposed to, and it's not that they can't do anything about it, they can actually do a surgery to replace the aortic valve, and typically what they use PICC valves for those. They can use Usually the most common one that they use, because pigs, they can just grab a valve from it and just inject it right, basically sew it right back in place, and then now you've got a functioning valve. Here you can see the movement of blood, and I've got a nice video for you guys afterwards that will show you the direction of blood flow and the way these valves work. So here you can see blood flowing in. This is blood flowing in from the superior vena cava, and I'll talk about these structures later on. Superior vena cava that are going to be filling up the right atrium. And as blood flows through, you can see in between, these are going to be our AV valves that are going to be zoomed in right next door. You can see blood flowing in, and as blood flows through, that'll allow these leaflets to open, and you can see the chordae tendineae are not very tight at all. In fact, they're very loose, and the papillary muscles are relaxed to allow blood to flow from the left atrium into the left ventricle. Now, the next portion of the cardiac cycle, again, we'll go into more detail later, but when pressures build up in the ventricle as squeezing takes place, that's going to shut those cuspids. They're going to shut it right back up, and you'll see that the chordae tendineae and the papillary muscles will be tightened. And that will hold those leaflets in place to prevent that from flying right back up, to allow blood to flow back in. Now, any dysfunction of the AV valves are going to create what's called stenosis. You're going to hear blood leaking back in, things that are heard during an exam, extra sounds during an exam where they want to listen to the different chambers of the heart. So these typically are things that fail less likely to fail than that of our semilunar valves. Here you can see our pulmonary valve taking place. If we're looking specifically at, yes, we're looking at our pulmonary valve. You can see there are no structures contained within. As blood flows through, flows in one direction, and when blood fills up in this area and pressure increases, that's going to cause the flaps to close right back up to prevent blood from flowing back in. So all of these valves, both AV valves as well as our semilunar valves, afford that unidirectional blood flow that takes place. Arteries and veins. Big thing about arteries and veins, arteries conduct blood away from the heart, as well as veins returning blood back to the heart. Do not confuse arteries and veins for carrying oxygenated or deoxygenated blood. That's the common thing that people will make that mistake on, that veins always carry deoxygenated blood. That's not the case. It's really what governs the name of an artery or vein is the direction of blood flow, whether to the heart or away from the heart. Arteries in general have thick arterial walls and will be able to be subject to high pressures because they're going to be the direct output of the heart. The one thing I'll talk about is going to be the aorta. The aorta is going to have blood coming out from the left ventricle, so there's going to be this onslaught, this rush of blood flowing through. So naturally you want to have thick walls that are going to be able to withstand the high pressures that are exhibited. Now once that blood makes it all the way down the course and making its way back into the veins and draining back into the heart, you'll see that the veins are going to actually have thinner walls and are going to have considerably far less pressure as it dumps blood back into the heart. To give you examples of arteries and veins, you can see our aorta, our pulmonary trunk, and then our coronary arteries. And I'll be able to show you that on the next slide over, where here you can see the pulmonary trunk is the direct output of the right ventricle. So here's our semilunar valve. This is going to be blood carrying away from the heart. So this pulmonary trunk branches off into the left pulmonary artery and the right pulmonary artery. So this is going to contain deoxygenated blood that's making its way into the lungs. So here, this is an example of an artery that's carrying deoxygenated blood. Now, the other artery in this case will be our aorta. It's going to be our biggest artery that's carrying blood out. So this is going to carry oxygenated blood through the systemic circuit. This blood is being sent out, and this is the aorta. You'll see that one of the first outputs of there is going to be the coronary artery. And I don't think you can see it on this slide. It's actually on the very back of the slide. The next thing is to look at the major veins. You have the vena cava, the superior and inferior vena cava, and our four pulmonary veins. And again, you can see that on the next slide over. So the inferior vena cava, let's see if we can see it from This slide over, you can be able to see it. Inferior vena cava delivering blood back from anything below the heart. Superior vena cava delivering blood down from anything superior, anything above the heart. All of that's going to drain back into the right atrium, and again, it's carrying deoxygenated blood. So, looking at the pulmonary veins are going to be sending blood back from the lungs into the left atria. So these veins are carrying oxygenated blood into the heart. And again, what governs them is the direction of blood flow. Veins going into the heart, arteries going away from the heart. So with this slide, you can see the input and output of the heart based on all that information, knowing that arteries deliver blood away, veins deliver back in. You can see the left heart with its input and output. Again, output for the left heart would be the coronary arteries, which is going to supply blood to the heart itself. I'll talk about that at the end of today. You'll see the other branches over here. I'm not going to have you guys really memorize these because, again, these are more anatomical things. Superior vena cava, inferior vena cava, and so forth. The things that I would like you guys to be very familiar with, maybe not so much the branches of the aorta, but know the big structures, the pulmonary veins, vena cavas, the pulmonary trunk. That's the big thing I want you guys to remember. And in fact, that's what your homework does. It helps you keep track of all the different structures and know the direction of blood flow. Why is that important? Because as we start to go into the cycle of the heart, I'm going to be talking about blood flow for the pulmonary circuit as well as the systemic circuit. And I want you guys to be really familiar with that, because when we get into our lectures next week, that wouldn't be the time for you to think, oh wait, which direction the blood flow is it again? Is it the pulmonary veins are going into which direction, pulmonary trunk is going where? You want to get a good handle of that, because once I start talking about that, you can easily fall behind when you're trying to figure out the orientation of this. Again, stuff that you would have talked about in anatomy, so this shouldn't be new information for you. The blood flow in the heart. Let's see if I can get this video to work. Plug this in first. Fairly short video. And then I got one more slide after that, and then I'll talk about a couple of coronary slides, and then we'll be done for that. Video on YouTube. Hear anything? Is there sound? There isn't any sound, okay? That doesn't make any sense. Well, regardless, you can at least see what's happening. I can describe everything that's taking place for you. You'll be able to see the chambers of the heart, the atria filling up. Then you'll be able to see the next phase where the ventricles are going to be squeezing, emptying blood out. So this is going to take us through the different cycles where the atria fill, while the ventricles squeeze. Now we're going to have the atria squeeze, dumping blood back into the ventricles. As the ventricles are going to fill. And then the next step is going to be the squeezing of the ventricles, allowing blood to flow out the semilunar valves. So we'll start to break down all the different chambers as you can see what's taking place. Our AV valves over here, AV valve over here. This would be our bicuspid, tricuspid. This is going to be our aortic valve, and this is going to be our pulmonary valve. And all of that, what's going to govern blood flow in unidirectional fashion from a right atria to right ventricle to the pulmonary trunk are going to be those valves. And what we'll talk about on Tuesday is what's going to cause the contraction. And as we start talking about the contraction that's taking place on the muscle itself, we'll learn about the pattern that's going to take place in the heart. the patterns that are going to be exhibited by the heart, and the cardiac cycle that ensues. So we'll be able to see the different electrical wave patterns that will take place. So this slide helps kind of draw out the movement of the blood for the pulmonary circuit as well as the systemic circuit. Here you can see everything taking place in series, the flow of blood as it flows through. Everything that I've drawn out for you in blue is going to carry deoxygenated blood, even though we know deoxygenated blood isn't blue. This at least helps you kind of point that out, because every image that I've ever been able to find always shows deoxygenated blood in blue and oxygenated blood in red. And here you should be able to follow that circuit when starting off at any point. The right atrium goes to the right ventricle to the pulmonary trunk, pulmonary arteries delivering it over to the lungs. We're going to see gas exchange taking place in the lung itself. This is going to be external respiration, which we'll talk about not next week, but the week after that, the Tuesday after. Pulmonary veins are going to be delivering blood, freshly oxygenated blood from the lungs, delivering that back to the heart, where it's going to dump back into the left atrium, or the left atrium to the left ventricle, over to the ascending aorta, down to the descending aorta, splitting off from arteries, arterioles to capillaries. This is going to be internal respiration that's going to take place. And then we're going to be able to see the veins coming back to the vena cava and starting back over at the right atrium. So here you can see that whole pathway as these take place in series, and how those chambers, both left and right atria, and both left and right ventricles that are going to pump back and forth. And you'll be able to see how that takes place on the next slide over. While this circuit is completing at the same time. So we'll be able to see how blood is moving in this fashion as we get the left ventricle and as we get the atria and the ventricles to take place at the same time. What happened?
We got lost.
Did I draw it in the wrong direction?
I don't know, you just didn't move your hands.
Yeah. So that's what's taking place is a figure eight, and that as blood is moving through, you're going to see how this is going to work in place. So we're gonna talk more about that when we look at our atria as well as our ventricles. We know that our atria are going to contract at the same time, our ventricles are going to contract at the same time, of which we know the left ventricular side here. You can see why, if you were to take a note of the left ventricular muscle wall, as well as the right ventricular muscle wall, you can see a clear discrepancy on the thickness of the muscle walls. Why do you think that is? Why is the left ventricle muscle pumps it out to the body, right? So it's got to be bigger, it's got to be stronger in order to deliver blood out through the entire systemic circuit, while the right ventricle, literally I just go right next door. That's all they need to do. So it doesn't have to be as strong. Hence, while the right ventricular wall is going to be thinner comparatively to that of the left ventricle. Coronary circulation, again, I'm going to be really quick about it. You can see our left coronary and right coronary, and this is going to deliver oxygen to the heart itself. So the question is, why does the heart need oxygen when it's carrying oxygenated blood through it? Well, only the very the small part of the endothelium, the inner layer of the heart, is actually going to be able to pick up enough oxygen. But as I mentioned earlier, the muscle walls are going to be thick, so they're going to have its own circulation in order to be able to supply, because heart never really rests. It's going to continually beat over and over again, so it needs to be able to have enough glucose and have enough oxygen to continually pump and be active. So naturally, the coronary circulation is going to deliver blood flow. It's going to be the first output in the aorta itself. And I'm not going to have you guys break down and take a look at the anterior or interventricular circumflex branches. Don't worry about that. Blood's going to, as it makes its way into the coronary arteries, that'll make its way into the heart tissue, and then it's going to collect that blood back up into the coronary sinus. So the coronary sinus is what's going to dump back right into the right atrium. It's going to deliver deoxygenated blood back to make its way back into the input of the heart would be the vena cavas. Coronary sinus dumps in as well, and that's going to make its way to the right atrium. With that, that tops it all up. All right? So I will see you guys on next Tuesday. Stuff is all uploaded for you guys to review over the weekend. And thank you for your attention. I will see you guys next week.